Take a look at a bookshelf loaded with heavy books. If you look closely, the shelf isn't perfectly straight. It sags in the middle. That sag is deformation, and it's the kind of thing a physics course usually ignores. A car spring compresses under load. A bolt stretches slightly when tightened. Solid mechanics is the study of how solid objects respond when forces act on them. In this course, we look inside the material to understand what it actually feels. This is episode 1, and we're going to build every idea from scratch, starting right now. Let's start with something you already know: forces. When you push on an object, 3 things can happen. It can accelerate. That's dynamics from your physics course. It can stay perfectly still. That's statics, where all forces balance. Or the material itself can change shape. It deforms. That's solid mechanics. Newton's second law still applies, but now we also care about what happens inside the object. So let's talk about the objects we'll be studying. In solid mechanics, we study structural members, solid bodies designed to carry loads. A bar carries forces along its length. We call that an axial load. A beam carries forces perpendicular to its length. It bends. A shaft carries twisting loads. That's called torsion. And a column carries compressive loads, forces that try to squash or buckle it. We'll start with the simplest case, a bar pulled along its length. To understand what that bar feels, we need to look at the force inside it. Here is the big idea: internal force. Imagine a bar being pulled from both ends by equal and opposite forces. Now imagine slicing the bar in half right at the middle. The left half still has to be in equilibrium. Something must pull it to the right. By Newton's first law, that internal pull P must equal the applied force F. That internal force is what the material actually feels, and it's always found by cutting and balancing. But the internal force alone doesn't tell us if the bar will survive. This is where stress and strain come in, 2 of the most important ideas in all of engineering. 10 kilonewtons through a tiny wire is catastrophic. The same force through a thick rod is nothing. Stress is internal force divided by the cross-sectional area. We write it as sigma equals F over A. The unit is newtons per square meter, which we call pascals. In engineering, we usually use megapascals. Strain measures how much something deforms relative to its original length. Epsilon equals delta over L naught, change in length divided by original length. It has no units. Stress tells us if something will break. Strain tells us how much it changes shape. Now let's see how these ideas frame the 3 big questions of this entire course. Every time we analyze a structural member, we're really asking 3 questions. First, will it break? This is the strength question. We compare stress to the material's limit. Second, will it deform too much? This is the stiffness question. We check strain and displacement. If a bridge is strong enough but sags a meter, it's still not a good design. Third, will it buckle? A thin column can collapse sideways even if the stress is low. We'll cover stability later in the course. For now, we focus on strength and stiffness. Let's see the full course roadmap before we work a problem. Here is the path we'll follow through this entire course. We start with axial loading, bars pulled or pushed along their length. Then torsion, shafts twisted by torques. Then bending, beams loaded sideways. This is the longest and richest topic. Then we combine all 3 into real-world loading scenarios. We learn to transform stress from one orientation to another. Moore's circle lives here. And finally, failure criteria, how to predict when a material gives up. Each topic builds on the one before it, so we take them in order, step by step. Now, let's put everything together with a real-worked example. A steel bar is 500 millimeters long and 10 millimeters in diameter, pulled by 20 kilonewtons at each end. Step 1. Draw the free body diagram and confirm equilibrium. 20 kilonewtons to the left, 20 to the right, they cancel. The bar is in equilibrium. Step 2. Cut the bar at the midpoint and draw a free body diagram of the left half. The internal force P must be 20 kilonewtons to keep this piece in equilibrium. Step 3. The cross-sectional area. The radius is 5 millimeters, so A equals pi times 5 squared, which is 78.54 square millimeters. Step 4, stress equals force over area. That gives us about 255 megapascals. Step 5, the bar stretches slightly under this load. That change in length divided by the original length is the strain. We need one more tool to compute that strain, the material's stiffness, and that's coming soon. In the next episode, we'll learn how to find forces and reactions in any structure, which is always step one in solid mechanics.